I'll share my screen. 1 second. Yeah, my screen is visible now.
Yes, sir.
Yeah, 1 second. NMOS and PMOS we'll discuss. Okay, NMOS and PMOS will discuss. Okay, so NMOS and PMOS, outline of NMOS and PMOS. Okay, NMOS and PMOS. Okay, so here basics. Okay, what are the basics we already studied that we'll see. Okay, basics of NMOS and PMOS. Okay, so these are the basics you need to know. Okay, then only you can understand the operation of CMOS. Okay, yeah, tell me in channel means in NMOS. In NMOS, channel is of what? Channel is due to what? Tell me. Channel is of what? Channel is due to what? Electrons or holes?
Holes.
Channel is due to electrons, no. N
Electrons.
channel. Electrons. Channel is due to electrons. Okay. In PMOS, channel is formed. Channel is formed. Channel is of what?
Holes.
Holes. Channel is of holes. Okay. And in NMOS, okay. In NMOS, substrate. What substrate you have in NMOS?
P-type.
P-type. P-type substrate is there. Substrate is nothing but lightly doped P-type material. Lightly doped P-type material. Okay. In PMOS, substrate is of N-type. Substrate is of N-type. Okay. And in NMOS, drain current, whatever the drain current is there, drain current ID, drain current ID flows from where to where? The electrons will flow from source to drain. There is a conventional current, that is drain current, that will flow from where to where? Drain to source. We already seen now. Electrons will flow, channel will be forming, and electrons will flow from source to drain. So drain current will flow from drain to
Drain.
source. Okay,
Drain
that's
to
why we
source.
call as sometimes we call this as IDS. IDS is nothing but drain to source. Okay, drain to source. And in PMOS, drain current. Okay, drain current ID. Drain current ID flows from where to where?
Source to drain.
Source to drain. Okay, flows from source to drain. Okay, source to drain. That means holes will flow from source to drain. The current will be same direction of hole movement, so it will be flows from source to drain. Okay, so these are some basics related to this. And coming to the symbols, okay, how the symbol will look like for NMOS and PMOS, symbol for NMOS and symbol for PMOS. Okay, so we'll see the symbol for NMOS and PMOS. Okay, NMOS and PMOS. Okay, so this is just a revision. So in order to understand about the CMOS, you need to know about this NMOS and PMOS. Okay, so this we already discussed, but just a revision type. Okay, yes. Yeah. See here. Next, symbol for NMOS and PMOS. So what is the symbol for NMOS? The symbol will be like NMOS. So let us take the NMOS. NMOS. Okay, so NMOS, the symbol will be like this. This is gate, and this one is drain, this one is source. Okay, and current will flow from where to where? Drain to source. Okay, this is ID. Okay, so this gives the current direction. Okay, this gives the current direction, drain to source. Okay, this is NMOS. Okay, or you can represent like this also, NMOS, no, the symbol for this, so NMOS, simply you'll represent like this. In CMOS, simply you'll represent NMOS like this. Okay, so this is gate, drain, and this one is source. Okay, so ID is flows from, so this is NMOS. Okay, so and drain to source. Okay, next, with respect to body, how we are representing, that means this is basically which type of MOSFET, NMOS and PMOS you are using in CMOS, either enhancement MOSFET or depletion MOSFET.
Enhancement MOSFET.
Enhancement MOSFET means what? Channel is not there. You need to develop the channel by applying a positive gate voltage for NMOS and negative gate voltage for PMOS. Okay, so here that means the symbol, another symbol representation is this one. Channel is not there, just breaking of this one. Channel is not there. Okay, and here this is gate. This is gate. Okay, and next drain, gate, and source. Okay, and this one is what? Bulk or body, a substrate. Okay, bulk or body or substrate. Okay, so this is nothing but a MOSFET, enhancement MOSFET. Okay, enhancement MOSFET. Okay, is this fine with symbols? Any doubt in this? NMOS.
No, sir.
Next, PMOS. Okay, so PMOS, if you see the symbol for PMOS, so once first symbol is it's showing the current direction. Okay, so this is gate only. So this one is gate, drain, and source. Okay, so here you can write source here. Here you can write source and drain, and this one is gate. Okay, so it will so current will flow from where to where? Holes will flow from source to drain. The drain current is also from source to drain. Okay, so basically in the CMOS you are using this one. Okay, this symbol, just this is NMOS. Okay, and this symbol also you are using for CMOS, for PMOS. Okay, just a bubble is there. Okay, bubble will be there, and this one is drain, not drain, this is source. Okay, so this is source. Okay, source will come first for the PMOS. Okay, this is source, and this one is drain, and this one is gate. Okay, gate. Okay, this is the current will flow from source to drain, ID. This is PMOS. Okay, and if you consider the basic with respect to this body, so body, so this will be like this. Okay, and gate, drain, source, and here this arrow is inside means what? Channel is due to electrons. Okay, here arrow is outside. Means what? Channel is due to holes. Okay, this is body or bulk. Okay, body or bulk. So channel is due to holes. That's why arrow is outside. Okay, so basically we are using these two symbols for CMOS circuits. These two symbols for CMOS circuit. Is it fine? Any doubt in this? Shall I move forward?
Yes, sir.
Okay. What about remaining?
Yes, sir.
Okay. Next you see. Next, ideal working of NMOS and PMOS. Okay, how the NMOS will work and how the PMOS will work, we'll see. Okay, ideal working of NMOS and PMOS. Ideal working of NMOS and PMOS. Okay, so first we will see NMOS. Okay, what is the ideal working NMOS? Okay, so NMOS, if you see, I am drawing the symbol for NMOS. So this is the symbol for NMOS. Okay, and gate, and this is drain, and this one is source. Okay, so here let us take the input voltage is A. Okay, input voltage is A. So you are applying, like, suppose if so, ideal properties, if A equal to 0. Okay, if A equal to 0, so that means drain to source will be act as open circuit. Okay, open circuit. So this is open circuit when A equal to 0. Okay, so this is open circuit. Okay, open circuit. And next so if A equal to 1, drain to source will act as short circuit. Okay, drain to source will be act as short circuit. So as you know, the transistor is acting as a switch now. So that means when you are giving 0, it is acting as a off switch. When you are giving as 1, it is acting as on switch. Okay, so these are the ideal working of NMOS and PMOS. Okay, similarly, if you take PMOS, just reverse of this. Okay, so that means here if you see, so this is the current direction, and here you can see the current direction also. Okay, current direction is from where to where, source to drain. Okay, so the current direction will be, one second, so current direction will be for NMOS, for PMOS, here you can give the current direction also for source to drain. Okay, like this you can give the current direction. Okay, so current direction you can give, or with the bubble also you can give, that is PMOS. Okay, and so if you see the ideal working of PMOS, here you have, so this is the current direction. Here you have source, next drain, gate. Okay, and so here if you take the input A. Okay, if A equal to what? A equal to 0, so source to drain is what? A short circuit. Okay, if A equal to 1, okay, source to drain is a short circuit, so it will be short circuit. Okay, and so this is short circuit, and if A equal to 1, source to drain is open circuit. Okay, open circuit. Yeah, tell me, am I audible? Is it fine now? Give response.
Yes, sir.
Okay. So these are the ideal properties of NMOS and PMOS. Okay, NMOS and PMOS. Okay, and next, if you see the input characteristics. Okay, so input characteristics are nothing but transfer characteristics we already seen. Okay, those are not input characteristics. Those are nothing but we call as transfer characteristics and output characteristics. Okay, so transfer characteristics of NMOS. Okay, transfer characteristics. Transfer characteristic for NMOS I am writing. Okay, for NMOS. So that means transfer characteristics is nothing but what? Output current with respect to what? Input voltage. Okay, so this is output current ID with respect to what? Input voltage VGS. Okay, so here what happens till cutoff region. Okay, so what is the cutoff region? Here this is the cutoff region. Okay, so till cutoff region channel is not forming. So that means when channel is not forming, the drain current is what? 0 only. Okay, drain current is 0 only, and after that channel is forming, so drain current increases after VTH or VT threshold voltage VTN. Okay, this is nothing but VTN. So after when VGS is crosses this VGS crosses VTN, then different conditions. So when VGS is greater than VTN, okay, so VGS is greater than VTN, so this is the condition, VGS is greater than VTN, channel will be forming, that is nothing but strong inversion layer. So this will be operated in which region? linear or saturation region. Linear or saturation region. Okay, that we have already seen. Okay, so that means if you see the NMOS, so this is the symbol for NMOS. So this is gate, and this one is drain, and this one is source. Okay, so that means here VGS, this is input voltage, is nothing but VGS. Okay, and output voltage is nothing but with respect to source, this is VDS. Okay, and there is a current flowing from drain to source, that is ID. Okay, VGS also we are giving positive only for NMOS. Okay, VGS also we are giving positive. Okay, and if you see the output characteristics, we already seen. So output characteristics, or we can call as drain characteristics. So what are the output characteristics? Here this is ID, and this is output voltage VDS. Okay, so here this is 0. Okay, this is 0. So when VDS is less than 0, okay, and so what is the cutoff region? So this is, let us take this is cutoff region. Okay, so cutoff region. So what is the condition? So VGS is less than VTN and VDS is less than 0. You are not applying any voltage. Okay, so this region is nothing but what? Cutoff region. Cutoff region. So cutoff region means what? ID is nearly equal to 0. There is no drain current. Okay, what happens? Again you are increasing. So you are increasing VGS. Okay, so you are increasing VGS. So here if you see, you are increasing VGS. Okay, so that means what is the condition? Channel is forming. VGS is greater than VTN, and VDS is small value, such a way that VDS is less than VGS minus VT, overdrive voltage. Okay, VTN, VGS is less than VGS minus VTN. So this will be operated in which region? Linear region. Okay, after that there will be non-linear. There is a channel is non-uniform, this is non-linear. After that it becomes constant. This is nothing but a saturation region. Okay, so what is saturation region? That means VDS should be greater than or equal to VGS minus VTN. This is nothing but saturation region. Saturation region. Is the the characteristics are fine?
Yes, sir.
Okay, so these are the characteristics. Just for this one, what for PMOS, just vice versa, means opposite. Okay, so here greater than will come, there less than will come. Okay, and all are negative means you will get the characteristics in the third quadrant. Okay, third quadrant. Okay, so that means so if you write the equations also, okay, current equations, drain current equations in different regions. Okay, we already discussed. Okay, so what are the drain current equations? So when in cutoff region, what is drain current? Cutoff region, what is drain current? There is no drain current, no?
0.
Channel is not forming. Drain current equal to 0. Okay, drain current equal to 0. Okay, in cutoff region. Cutoff region. Okay, and next in linear region. In linear region. Okay, in linear region, ID equal to Kn by 2. Okay, Kn by 2 into VGS minus VTN into VDS minus VDS square. Okay, VDS square. Okay, and Kn equal to what? Where Kn equal to what? Where Kn equal to Kn, when Kn equal to what? Mu n COX W by L. Mu n COX W by L. Okay, and in saturation region. Okay, saturation. So id equal to kn by 2 kn by 2 into vgs minus vtn whole square. Okay, if you consider channel length modulation, then you will get 1 plus lambda into vds, lambda into vds. Okay, if you are not considering, means you are getting only this one. Okay, where kn is, what are the units for kn? Amperes per whole square. Okay, and w by l, w by s is nothing but aspect ratio, aspect ratio, that is width to length ratio. Okay, of channel, of channel. Okay, so this is unitless, unitless. Okay, and next mu n is nothing but mobility of electron. Okay, so this is centimeter square per volt second. These are the units. Okay, and next COS is nothing but the whatever the silicon dioxide is there, that capacitance. Okay, capacitance for the dielectric. Okay, so this is farad per centimeter square. Okay, these are the units. Okay, so these are the units. And next we already seen the different regions of operation and what are the conditions. Okay, so if you see the different regions of operations, what are the operations for NMOS? For NMOS, what are the regions of operations? When VGS is less than VTN, which region? Cutoff region. Okay, and when VGS is greater than VTN, again two conditions are there. Okay, depends on this VDS. Okay, so when VDS is less than VGS minus VTN, which region? Linear region.
Linear.
Okay, and when VDS is greater than
All
VGS minus VTN, which region? Saturation region. Saturation. This is means in linear region or non-linear region, both conditions are same only. That we have seen the triode region. No, triode region means that same conditions. Okay, and whereas in PMOS, what are the conditions? VGS should be greater than VTN. VGS should be greater than VTN. Which region? Cutoff region. Okay, and VGS is less than VTP. VTP here, VTP. Okay, threshold voltage with respect to PMOS. Okay, so again conditions, when VDS is greater than VDS is greater than VGS minus VT, VGS minus VTP. Okay, which region? Linear region. And when VDS is less than VGS minus VTP, which region? Saturation region. Saturation region. Okay, so these are the conditions. Okay, and next so if you see the comparison of NMOS and PMOS, okay, NMOS and PMOS, what is the comparison? Okay, that we will see. Okay, so comparison of NMOS and PMOS. Comparison of NMOS and PMOS. Why I am telling again means these we are going to use in the inverters CMOS concept. That's why you need to know about the NMOS and PMOS. Okay, that's why I am revising these concepts. Parameter, and next NMOS, and next PMOS. Okay, so here if you see symbol, first symbol. Okay, what is the symbol we are using in the CMOS? Okay, this is the symbol. Okay, this is a gate, drain, and this is source. Okay, and next here this symbol we are using, bubble will be there for PMOS. And what are the terminals? Gate is common. Here source will come, source and drain, source and drain. Okay, and coming to the structure. Okay, structure, What is the structure in NMOS and PMOS? Okay, structure. Okay. Next is structure. If you see the structure, source and drain. Source comma drain. Those are nothing but which type in NMOS? N type. Okay. And bulk or substrate. Bulk or substrate. This is in which type? P type. Okay. And here source and drain. These are P type. And bulk or substrate. Bulk or substrate. These are N type. N type. Okay. And majority carriers. Majority carriers. What are the majority carriers over here? Electrons. Channel is formed due to what? Electrons, no? Here what are the majority carriers? Holes. Okay. I told you in a FET, MOSFET, in any JFET or MOSFET, the current is due to both only majority carriers, no? Not minority carriers. The current is due to majority carriers. So that's why this is NMOS is there. This is nothing but N channel. So N channel, the name is there. So in this channel, the charge carriers are electrons. Okay. This is P channel. P channel means what? The charge carriers are holes. Okay. Majority carriers are holes. Okay. And next if you see direction of the current. Direction of current. Where to where it will flow? Tell me. In NMOS, what is the direction of the current? Drain to
source.
Drain to source. Drain to source. Okay. And here source to drain. Source to drain. This is the direction of the current. And size. Coming to the size. Okay. NMOS size is smaller compared to PMOS. That I will tell you why it is smaller. Okay. NMOS size is smaller compared to PMOS. Okay. So this is one of the interview question they will ask, why the NMOS size is smaller than the PMOS and how much times it is smaller. Okay. So this is very important. And PMOS size is larger compared to NMOS. PMOS size is larger compared to NMOS. Okay. And next, coming to the working. Okay. Coming to the working. NMOS and PMOS. NMOS and PMOS. Okay. Coming to the working. If G equal to 0, ideal cases, okay, ideal cases with G equal to 0, NMOS will be off or on? Off. And if G equal to 1, NMOS will be on. Okay. And if G equal to 0, PMOS will be on. And if G equal to 1, PMOS will be off. Okay. And next you see operating speed. If you see the operating speed, this is faster. We know that mobility of electrons is more than the mobility of holes, no? So this is faster in nature and this is slower in nature. Okay. So this is about the comparison of NMOS and PMOS. Is it fine? You understood?
Sir, why is it faster and why is it slower?
Faster means this mobility of electrons is more than the mobility of holes.
Okay.
Mobility actually, like I told you in the semiconductor physics, basically hole will not exist. Basically hole will not exist. Okay, so hole is nothing but suppose like electron is flowing like this, so electron will move. Okay, so electrons are flowing like this. Suppose so electrons are so one electron is there, electron is moving like this means here one vacant position is available. Okay, from here to here electron is moving. Okay, one vacant is position is happening. Okay, so like this it is moving means they assume that the vacant position is nothing but they assume that hole. So electron is moving like this, how the hole will move?
Okay.
Opposite direction, no? So that means
Opposite.
hole, practically holes will not exist. The absence of electron is nothing but hole.
Okay, sir.
Okay, so from this you can conclude that electrons will move faster than the holes. Okay, mobility of electron is more than the hole, so that's why this NMOS are faster and PMOS are slower. Is it fine now?
Yes, sir.
Okay, now why NMOS size is more than the PMOS? Okay, this is one of the interview question they will ask in the interview. Okay, so you need to justify that. Okay, justify his question. Okay, with your answer. Okay, so what is the question? Why PMOS size is more than NMOS? Okay, see, PMOS size is more than NMOS. Okay, now so PMOS, so here if you see the PMOS, what are the majority carriers?
Holes.
Majority carriers are holes. Okay, majority carriers are holes. And NMOS, what are the
Electrons.
majority carriers? Electrons. Majority carriers are electrons. Okay, so majority carriers are electrons. Okay, so that means electrons are having 2.5 to 3 times mobility compared to holes. Okay, as I told you, no, mobility of electron is more than the mobility of holes. Okay, how much of mobility is there means electrons. Okay, electrons are having uh, 2.5 to 3.5 times mobility compared to holes. Okay, compared to holes. Okay, 1 minute. Okay, so here if you consider the symmetry, okay, symmetric CMOS inverter. Okay, symmetric CMOS inverter means some parameters you can approximate. Okay, some parameters you can approximate, that is nothing but symmetrical CMOS. Okay, so for symmetrical CMOS inverter, that will discuss in the further classes. What is the symmetric CMOS? For symmetric CMOS inverter. So here so mm, so kn by kp equal to what? 1. Okay, there is a kr. Okay, will like kr equal to, this is a relative thing, kn by kp will approximate to 1. Okay, there we approximate to 1 when we calculate for the PMOS, that is noise margin. Okay, noise margin and VIH. Okay, VIL. Okay, VIH and VIL, there you will get a big formula. So but in problems we'll assume that that is a symmetric CMOS, symmetric inverter. We'll assume some assumptions. That assumptions are nothing but VTN, that is equal to mod of VTP. Okay, these assumptions we will consider. Okay, so that means kn by kp equal to what? 1. This is the assumption. Okay, for symmetric CMOS. Okay, symmetric CMOS inverter. Okay, CMOS inverter. So here what is kn? Kn equal to mu n COX W by L of N, W by L of N, and this Kp equal to mu P COX W by L of P. Okay, this is equal to what? 1, equal to 1. Okay, so here mu n by mu p, so mu n by mu p, mu n by mu p equal to, so this is having mu n is equal to 580 centimeter square per volt second. This is a constant value. This is the mobility of electron. Okay, and mobility of hole is 230 centimeter square per volt second. Okay, this is constant. So you will get around, if you calculate this, you are getting 2.5 times. 2.5 times. Okay, so that means from here, anyway, this COX is nothing but oxide capacitance. This is same thing, same value. Oxide capacitance is same value. So from this, W by L of P by W by L of N, that is equal to what? That is equal to mu n by mu p. Mu n by mu p. So this is equal to what? You are getting mu n by mu p equal to what? 2.5 to 3 times. 2.5 to 3 times. Okay, so that's why. So how much of size it will be more, means it will be about 2.5 to 3 times more than the NMOS. Do you understood how you got? Give response. Hello.
Yes, sir.
Understood, no?
Yes, sir.
Okay.
So for conclusion, due to the mobility of electrons greater than mobility of holes, the
Yes.
width and length of what is it?
Yes.
MOS
Mobility.
will be greater.
Yes, mobility. This value is constant only, 580 centimeter square per volt second, and mu p is 230 centimeter square volt second. So from this you will get around 2.5 to 3 times. Okay, so that means you can say that mobility of electron is more than the mobility of hole. So if you consider a symmetric CMOS circuit, these are the assumptions. That means KR you consider as Kn by Kp, and both threshold voltages are equal. Okay, both threshold voltages are equal. So if you substitute, you will get that means 2 to 3 times more.
Yes, sir.
Okay. Is it fine now? Shall I move forward?
Yes, sir.
Okay. Okay, NMOS inverter I will tell you in the next class. So we'll wind up now.
Sir, what about asymmetric CMOS? Like, do we have any condition for that also?
Asymmetric means basically like if you are taking asymmetric CMOS, when you are calculating this noise margin and VIL and VOL, you will get a larger value. Just 1 second.